says balance the following chemical equation. Le2 Se solid plus SO2 gas yields SSE2 gas Le2O. Okay, so what is going to be the first thing that we need to do? What is going to be the first thing that we need to do? Okay, not all you guys yell at me at once. Cassandra, to balance a chemical equation, what is the first thing that we need to do?
List what we have on the left-hand side and how many of each.
Okay, so we need to list what we have. Let's see, so we have Li, we have Se, we have S, and we have O. Okay, how many Le's do we have on our reactant side?
2.
How many S's do we have on our reactant side?
1.
How many S's do we have on our reactant side?
1.
How many O's do we have on our reactant side?
2.
Okay, now on our product side, how many Le's do we have?
2.
How many SE's do we have?
2.
How many S's do we have?
1.
How many O's do we have?
1.
Okay, so the law of conservation says what we put in, we must get out. So what does that mean? What do we need to do?
Make sure we have the same number of each on either side.
Okay, so we need to try to make sure that we have the same number of each on either side. And we can do that by changing the coefficients. The coefficients are the numbers that would be in front of the compounds that we're looking at. So how can we change the coefficients so that they match up on both sides? So where should I start at? Lithium looks good, doesn't it? 2 on 2. So we don't need to worry about that one. What about our SCs? We have 1 and 2. So what do I need to do so that I have 2 on both sides? Gabriella, what do you think I should do? Multiply by 2. So what am I going to multiply by 2? Where am I going to put that 2 at?
You're going to put it on the left side in front of the Li.
Okay. So right here?
Yeah.
Okay. So if I do that, that means now I have 2 SEs and I have 4 lithiums. Okay. Darn it. Okay, so now my SCs are good, but now my lithiums are not. Okay.
So go over to the right side and put a 2 for the lithium oxygen.
Okay. So we're going to put a 2 here. Okay, so then that gives me 4 LEs. I have 2 oxygens. Okay, isn't that what we wanted? Everybody's happy?
Yes.
Okay, and so the way I would do this is, so now I can use Chem 101. So let's full potential. So I take my 2, put it in front of here. So I put a 2 here. And I put a 2 here. That's me. Clear. Okay, and then I should be able to submit it. The other ones are fine the way they are. Let's see, it doesn't give me a submit button. Okay, questions? Samantha, does that help? So he said yes, but what is the but? Oh, on homework 4, my bad. I guess that makes it a little hard. Let me get homework 4 up. Give me a second. Sorry about that, Samantha. You said 12. Ah, yeah, this one is a little hard. So we've kind of talked about the meniscus in the lab. And that's what we're kind of looking at, right? So this is basically showing you our burette. A burette is, let me show you, I'll draw what a burette really looks like. Let's see, or I should say what it would look like if I was artistic. Okay. Okay, so it's this really long tube that has gradients. So at the very bottom, it'll have a gradient, and they have gradients going up, right? And that's what is being represented in the figure next to me, are the gradients. They really want to pay attention to the gradients. And so burette works is that it has what we call a stopcock at the end, and we twist it. It's just a valve, so that allows liquid to flow through it. And so you can kind of control how much liquid flows through it. Okay, and so they're saying that if your burette reading started at 11, so at the top, this is going to be 11, or not 11, but, and then at the bottom, it's going to go down to like something like 50, right? So, and at the very, very top, it'll be like at 0 up here. So from 0 to 50, that would represent that full volume of the burette. So here you had a reading that was under 11, right? Or above 11. So in this case, we would go where the meniscus is. Okay, so if we went where the meniscus is, this guy would be, what would be our starting point? Eleven point what?
2.
11.2. Okay, so we're saying we're starting at 11.2 mils. Now, and we're going to drop it all the way down till we get to, this would be the final volume, 28, right? So, yeah, excuse my horrible drawing. So again, we want to go where the meniscus is. The meniscus is the low end of the liquid. So we go 28. So how would I calculate the volume that's been delivered? If I ended at 28, but I started at 11.2, how much liquid would I be having in my container that would be collected down here?
$16.8.
Okay. And how did you calculate that?
Subtract 28 from 11.2 from 28.
Okay. So I have 28 minus 11.2. And you said we get
16.8.
16.8.
Yeah.
Okay. So then I would enter that value here. Okay. Piece of cake. And so your values may change. So you may want to pay attention to your values because they may be different than mine. Okay, so we're talking about seg figs here. Okay, so last time where we left off, I believe we had talked about addition and we were just getting into multiplication. We did a little bit of examples for multiplication. So I want to see how much you guys remember about the addition. The addition seems to be a little more complicated than the multiplication. Okay, so let's see. Let's say we have okay. So we're adding these numbers together. Okay. So if I was doing addition, for the very first number, where does significant ends and uncertainty begins?
Isn't the whole thing significant?
The
So
whole
it
thing
ends
would
after
be-
the 8?
That is correct. So I draw a line there. Okay. What about the second number? 10.02
After the 2?
after the 2. What about the third number?
After the 1?
After the 1. So we're just going to keep that pink line drawn, same pink line. And what about the fourth number?
I would think after the 3, but I remember you saying if we write the decimal and write the zeros, then they're important.
That's right. That is correct. So it would be after the 0. So again, it would be that orange line. Okay. So because we took the time to put the decimal and then we put the zeros afterwards, that means that they're going to be important in this case. What about the last number?
Also after the 0?
After the 0. Okay. So we draw that line. That one's purple. So for those who may be colorblind, use letters as well. We have A, B, and C. Okay, so since I have A, B, and C, okay, which one, first off, which is the farthest to the left, A, B, or C? A, that is correct. A would be the furthest to the left. So another way of looking at it is, or more practical way of looking at it, which one has the least amount of significance that are showing? That would be A, right? Because we're not going as depth in the numbers following it as A is. So A would have the most uncertainty associated with it. Okay, so we're going to use A as our determining factor, that line right there. So what we're going to do is go ahead and add them up. Okay, so if we go ahead and add this up, let's see. 8 plus 0 is 8. 5, 8.5, 2, 3. Okay, so this line tells us where significance is going to end for our answer and which number we're going to use to determine whether we're going to round up or round down. So significant ends after the 8, right? So we want our value for significant figures, we're going to have a number that is 1 decimal or 1 digit after the 8. I mean, sorry, let me say that again. We're looking at the 8 itself, and we're trying to decide whether or not we're going to round it up, or leave it alone. And then this is where we'd have significance. So in this case, we'd have 4 significant figures for our final answer. So now we need to look at the number next to it, right? And the rule is if it's 5 or greater, let's say if it's 5, if it's greater than 5, we round up. If it's exactly 5 and there are no numbers following it and lower, we leave it alone. Okay, so if it's greater than 5, we round up. If it's exactly 5 and there are no numbers following it, we leave it alone. Okay, so in this case, are we going to round up or are we going to leave it alone?
You're going to round up.
I'm going to round up. So my answer is going to be 3.25.8. You said round up, my bad, 0.9. Yeah, you know, it feels like a Monday morning to me. My coffee hasn't set in yet. Okay, so that would be my answer. Okay, now if this number was exactly 5, let's say we had zeros here. If this number was exactly 5, what would we do in that case?
You would leave it
Leave it
alone.
alone.
I would leave it alone. So then in that case, in this situation, I would get 3.25.8. Okay, so does that make sense?
Yes.
Okay. Okay, so that was addition, right? So let's do some subtraction real quick to make sure that you guys got a clear understanding with that, and then we'll go back to multiplication because I know that's where we stopped at. So let's say we have this number. Okay. Okay, so here we have these two numbers. Where does significant ends with the first number?
After the 3.
After the 3. So let's draw a line there. And then where does significant ends after the second number?
After the 1. The
After
last
the
one.
1. Okay. So which line am I going to keep? A or B?
A.
Okay, so we're going to keep A. Okay, so let's go ahead and do the subtraction. Okay. So what would be my answer? The final answer? And what am I going to use to round or determine whether I'm going to leave it alone? Round up or leave it alone? So which number am I going to use to round up or
You're going to
leave it
use the
alone?
7 to round up?
So I'm going to use the 7. Okay.
Mhm.
So, and you said we're rounding up. So the answer would be 2,000, right? And we don't want to forget these zeros because they're placeholders. They let us know that we have 2,000 and not just 2, right? You guys see that? Are there any questions?
I don't know if I really understand the math to get that answer.
Okay, that's a good question, or that's a good statement there. Okay, so the first part is we did the math, subtraction, right? And because this number here, if we look at the number, there's not a decimal at the end. Did you notice that?
Yeah.
Okay, so that tells us that these zeros, they're not really sure about those zeros, right? So this number could really be, it could be 2,300 or 2,799, right? But they just rounded up to 3 because they weren't 100% sure about that number, right? So because they didn't put a decimal following it, that means that these zeros here, they're uncertain. We're not 100% sure about it. It's like you get those really cheap scales and they just give you the first number and all of the other numbers they're kind of guessing at. Have you seen that? Like those scales that you weigh yourself on?
Yeah.
Okay, so that's essentially what we have here. We have a scale that is only giving us whole numbers. So we're not really sure. That could be 2,975. It could be 2,755. It could be 2,577. It could be anything of those. It could even be 3,200, right? And we wouldn't really know because that first number is the only number that we see, okay? And because that's uncertain and we're using a number that is more certain to sit there and subtract it, because let's say you weighed something at one place and they weighed it at another, right? They weighed the remaining of it at another, then you're going to have two different numbers that you're working with, one that is very uncertain and one that is more certain. And so we have to go with the one that has the least amount of certainty. And so that's why we have to pay attention to this very first number, because it's less certain than the second number. So does that make sense?
Kind of.
Kind of. Okay. So because that first number has more uncertainty, because we're not sure whether it's really 3,000 or if it's 2,577, we have to make sure that we built in that uncertainty into our answer, right? Because we're not 100% sure, because if it's 3,000, if it's 3,300, right? This number is going to be well above that, right? But if it's 2,501, right? It's going to be well below this, right? And so we're saying that whoever looks at this, we have uncertainty as well. We're trying to give you a ballpark figure, right? Roughly what it's going to be, And so that's what we're trying to do as well. So we know that we only have one number of certainty. That 3 is definite. We know that that is the number that they're giving us because that was the number that was given and all of the other ones are zeros. By them putting those zeros there and no decimal, they're increasing that uncertainty, okay? And so when we subtract the number that's more certain, we have to increase that uncertainty because we're not 100% sure about that number itself, okay? So when we got 1,709, well, that's going to be a ballpark figure because, like I said, this could either be, it could be 3299 or it could be 25001, right? So it could be anywhere between there. So by us looking at this number here, we're saying, okay, this number is greater than 5. So then we're going to round this up. And we're going to say we still have uncertainty. We're not putting a decimal point here. We're just putting 2,000, and that's it. To let us know that we still have uncertainty associated with this, but this gives you a rough estimate of how much this could be. Does that make sense?
Yeah, that makes sense now.
Yeah. Okay. So let me add another layer. So we're doing multiplication now. So when we talked about multiplication, we had talked about using the number that has the least number of significant figures. Okay, so okay, which one of these numbers have the least number of significant figures?
The 9?
The 9. It has one significant figure, where the first one has 2 significant figures, the second one has 3 significant figures, the 9 has 1 significant figure. So if we do this multiplication, what's going to be our answer? Normally. And then we'll talk about rounding. What is 6 times 9?
54.
Okay. Okay, so we have a number that's 54, but we said that we only have one number of significant figures, right? One significant figure. So then what would be my answer?
Doesn't it just stay as 5?
Would it stay as 5 or would it stay as
50?
50? It'll stay as 50. We're not going to put 5 because we take this number here would be used to round. So we're going to leave it alone, right? So then we drop that number to a 0. And then this guy becomes 50. And that's it. Round down in this case. Okay. You guys see that?
Yes.
Okay. So, and the reason is the same reason that we had talked about, is that uncertainty. This guy could be, really, it could have been 8.995. It could be 8.501. So it really could have been an 8 there for that 9, or it can't be 10, but it could be something along those lines, and that would change our value. So we're just trying to pad our numbers just in case that we're off. So we're giving that uncertainty that's going to be associated with it. Okay, so let's see. And let's add some division to the multiplication. So division is going to be exactly the same way. So again, we're just going to be looking at the number that has the least number of significance. Okay.
So this one kind of confused me, but would it be like do all the multiplication on the left and then divide by the 3.0? So it would be 5.0 divided by 3.0?
Okay, so multiplication on the left. So then that would be, we look at our answer. So we go ahead and do it. So that'll be 100. So that's 600. 600 divided by 3.0 be 200. How many sig figs should I have?
Just one.
Just one sig fig. So the answer would be as is. Okay, if I had this, then my answer should be what? How many sig figs in that case?
4.
4 sig figs?
Or no, sorry, still 1, right? Because you're looking for the least.
The least, and is there just one? What would this be?
It would be a 2.
2.
That would be 2. So then I'd have to put my answer in scientific notation. So it'd be 2.0 times 10 to the second power, right? So then that would give me my 2 sig figs. Because this number, we're having significance up to this point right here. In this case. Okay, questions? Concerns? Okay. So what happens when we have multiplication and division and subtraction and addition? What is that rule? P something, P cash, P mash, pip dash. You guys remember that rule? Oh, PEMDAS. Okay. So we're going to be using PEMDAS, right? Okay, so let's see. Let's say we have okay. So here's our question. So what is the first thing that I want to do? Where am I going to start? According to PEMDAS.
Wouldn't you start in the parentheses?
Okay, I'm going to start in the parentheses. Okay, so then if I look at this, I have 200.0, which has how many sig figs?
5. I mean, sorry, 4.
4. And I'm subtracting 150. Oops, there's no decimal. So if I was drawing a line, where would the line be drawn between these two? 200.0. Would it be there?
Yes.
Okay, and the 50? I mean, sorry, the 150
After the 0.
after the 0? Are you sure?
Oh, I'm sorry, after the 5.
After the 5. Okay, so if I do this, I do my subtraction, I get 50.0. So if I determine my sig figs, I'm going to be looking at this number. Am I going to round up or am I going to leave it alone?
Leave it alone.
I'm going to leave it alone. So my answer is going to be 50, right? With only one sig fig. Okay, so now what do I do? So I have 50 here. This represents 50. With one sig fig. Decimal point there. Oops. So what would be the next order of operation that I would do? My choices are multiplication or addition.
Multiply?
I multiply, okay? So 50 times 5.0, that's going to be what? $50 times 5.0. And how many sig figs should I have?
Two.
Are you sure? Because 50, how many sig figs in 50?
1.
There's one sig fig, right? So if there's only one sig fig, I should only end up with how many sig figs?
1.
1. Okay, so I have 50 times 5.0 is going to be what? Normally it would be 2,000. I mean, not 2,000. 250, right? So if I need one sig fig, then this number should be
0.
So you're saying I should change the 5 to a 0? So it'll be 200? Is that correct? Because I want one sig fig? Or am I going to round up?
Don't you leave it like that? Because the number next to the 5 is a 0?
That's right, because it's an exact. So this number we'd be using for rounding. Since this is exactly 5, I have to leave it at 200. Okay, so this means that this guy is 200 now instead of 250. So if I add 25 to that, 25, say 25 added to that, 25.00. Okay, so where would I draw the line here? Where would the lines be drawn? For the 200?
Right after the 2.
after the 2.
Right after the 2. Okay, and what about the second one? Where would the line be drawn?
After the second 0.
After the second 0. Okay, so we add this up. We get 2, 2, 5.00. And what number am I going to use to determine whether I'm rounding up or leaving it alone?
The second 2.
The second 2. Okay, so what am I going to round it up or am I going to leave it alone?
Leave it alone.
Leave it alone. So my answer is going to be 200. So 200. Okay, so now all of this here is going to be 200. Okay, and now we're dividing by a number that has 1 sig fig, and we're dividing it by a number that has 4 sig figs, dividing it by 5. So what is going to be my answer? So we have
Would it be
200.
4?
That's right. 4, just 4 or 4.000. So it's just 4 like that? Yes, it is just 4 like that. Okay, that would be my answer, 4. Okay, you guys see how that changed our answer quite a bit? Because at each step, we had to take in consideration how we calculate significant figures, right? So had we not taken in consideration how we calculated significant figures, we would have ended up with a totally different answer. Does that make sense? So sig figs will play a part in your final answer. So you want to pay attention to that on the exam, because you will definitely get a question like this on your exam. Which I will be posting up a practice test for you guys probably on Sunday, this Sunday. And then you guys will have, again, this is done at self-paced, although I'm starting to worry because I'm looking at how many people have started the assignments, about the self-paced thing, but that's what I agreed to. And so we'll see what works out. I may see all of these people in the spring, face to face or whatever. So, questions? Okay.
Can we do another one?
Oh, go ahead. I'm sorry.
I'm sorry. Can we do another one similar to this?
Yeah, we can. Let me add a page. Okay, so let me think. Let's do. Okay. Okay, so where are we going to start? Don't you guys all yell at me at once. There's too much talking going on.
Do we just start in the parentheses again?
Starting in parentheses again. Okay, so we're in the parentheses. Are we going to start with the multiplication or the subtraction?
The multiplication.
Okay, so 2.000 multiplied by 50.0. So how many sig figs should we get from that? And what should be my answer? Mind if I drag this down? One sig fig, 7 sig figs, 25 sig figs?
3.
3. Okay. So we get 3 sig figs. So this is 100. So that's 3 sig figs, right? With the decimal. Okay. So minus 55. So if we do that, so that's 100 with 3 sig figs and 55. Where would I draw my line?
After the decimal?
After the decimal. Okay. So my line would be here. So we have nothing after it. So kind of stuck with what we got, right? So we have 2 sig figs out of that. So right here, this guy's 45. So what do I do next?
Multiply it by 8.00.
Okay, we multiply it by 8.00. So my answer should have how many sig figs?
Two.
2. Okay. So what is that? 3 something?
$360, but because we only have 2 sig figs, it would be 36, right?
No, it is still going to be 360. Remember, we use the zeros as placeholders. Don't drop those zeros. Those zeros just serves as placeholders. This is still 2 sig figs, right?
Okay.
Okay. Don't forget that. That's really important. That's the biggest mistake people make. Think of it like this. I always like to think of it like money. If somebody owed you $360 and they only paid you 36, and they say, okay, we're even, right? What are you going to say?
Of course not.
You're going to say, give me my money, right? So the zeros serves as placeholders, and so we want to make sure that we keep the same amount of placeholders that we need. Okay.
Got it.
Okay, so now we have 360 plus 20.5. 60 plus 20.5. So where do I draw my lines at? For the first number, where would
After
the
the
line be
6.
drawn? After the 6. And for the last number?
After the 5.
After the 5. Okay, so which one am I going to use? The red or the red?
Red.
How about the red or the green? Let's see if I can get the green to work. There you go.
The red.
Okay, we're going to use the red. Or we'll call this A. So we're going to use A. Okay. So let's go ahead and do the math. So we have 3.
380.5.
9.5. Okay. So what number are we going to use to round?
Wait, Dr. Henry, how did you get 339.5?
Oh, sorry, 239.5. My bad. Oh, wait a minute. I'm doing addition.
No, we're adding, so it would be 380.5, right?
Yes, thank you. One day I'll remember what I'm doing here. So I'm just trying to keep you on your toes.
Making sure I'm paying attention.
That's right. Okay, so we have 380.5. So are we going to round or are we going to leave it alone? And what number are we going to use?
You're using the 0, so we would leave it alone.
Okay, we're using the 0, so we're going to leave it alone. So then how many significant figures should my answer have?
2,
2 significant figures. So my answer should be,
38.
is it going to be just 38? Remember what I said about the placeholder?
380.
380. Don't cheat yourself out of that 10, right? That's 10 there. So 380. Okay, so we have 380 divided by 2.000. So my answer should be, how many sig figs should I end up with? Two, that's right. We should end up with 2 sig figs. So then my answer is going to be 190. With 2 sig figs. Piece of cake? Yep, no?
It's coming along.
It's coming along. It's a work in progress. And the biggest thing, the biggest mistake that all students make is forgetting to keep the placeholders. You need those zeros as placeholders. Always think about money, right? So if your answer is going to be $3 million and you get $3, you're going to be really pissed off, right? If you think about money, somebody owe you 3 million and they only give you $3. One day, that's what I should do. I should make a bet with students. Okay, so I want you guys to figure out this problem. And if you figure it out correctly, you get the money, right? Or say, if you figure it out, you get the money. And then we'll see how much money they get at the end. With the right sig figs. And it'll be like $300 and $3, right? Or $300 and 30 cents, you know. Okay, you guys good? Ready to move on?
Yeah.
Good. Okay, so we've talked about sig figs. And again, sig figs deals with uncertainty. It helps us understand that concept of uncertainty, right? And so if we're getting data from one point, from one group, and we're sharing that data with the stuff that we're collecting, and that group has a crappy, scale, then we have to take in consideration the uncertainty that's associated with their data points when we're adding it to our data. So it's going to make our data a little less certain because we're taking into account their data, okay? And we want to do that in science so that we make sure that our audience knows that there's some uncertainty involved in it, and we're taking that in consideration. It builds confidence in what we're doing. And so we can accommodate for those errors, you know, by looking at the uncertainty that's associated with the information. Okay, so a lot of you guys are planning to go into nursing. That's why I think a lot of you guys are taking this course. And so there's a lot of uncertainty when we talk about patients and how much meds. So we have to take in consideration like weight and size to kind of figure out how much medication an individual should be taking, or a ballpark figure, right? And so a lot of the medications are based upon size. You know, somebody who's really, really tiny isn't going to be taking up, you know, taking as much medication as somebody who weighs, you know, 1,000 pounds. And so we have to take that uncertainty into consideration when we're prescribing medication and things like that as well. So are you guys with me so far? And
Yeah.
so, but we also know that meds are not tailored to one individual, right? So somebody who weighs 100 pounds and somebody who weighs 120 pounds aren't going to be taking different quantities of that meds. So we have that range that's okay for that person who weighs 100 and that person who weighs 120. So that really comes into play with a lot of things that we do. We just don't recognize that we're doing it consistently. Okay. So exact numbers, if the number is exact, then that basically means that there's no uncertainty associated with it, right? That number is exact, it's perfect, right? So we don't have to worry about the uncertainty associated with it. But if we're introducing uncertainty into it by adding an uncertain number into it, then we can't use that exact number as means of significance, right? Does that make sense? We have to use the one that we're uncertain about as determining our significance. Okay. Okay. So this is an example. Here we have this ruler, right? This, which is not showing up. Okay, there we go. Okay, so right now we have two rulers, and in this case we have a lot of uncertainty involved in it because there's no gradients on the scale, right? So we have this ruler that has nothing on it, and we have another ruler that has nothing on it. Can you tell me how long the wooden stick above is?
Only by describing it.
Only by describing it, right? So you can only give me a really rough estimate of how much it is, right? So if they say that the bottom one is a meter stick, so how long is this guy based upon this meter stick?
A little more than half the meter.
So it's a little more than a half a meter, right? Based upon if that was a meter stick. And so you couldn't give me that uncertainty because you don't have the gradient. Where if we have the markings, we can get a little bit better with that uncertainty. Does that make sense?
Yes.
And then if we have even more markings, we can get even better with that uncertainty. Right? So, and then if we have even better gradation, we can get even better with that uncertainty, right? And so by looking at it, so that first person had a really shoddy, we have a meter stick that has no gradients, and this person had the really top line of the meter stick, right? They had the Cadillac of the meter sticks, right? So, and in reality, this is what we deal with every day. So depending on the medical system that you're working with, your scale may not be as accurate as the scale that's being, you know, used in Beverly Hills, right? So we have to be aware that there's going to be uncertainty involved in numbers that we're getting, that we're acquiring from individuals, right? If we're in the medical field. Or if we're in science, you know, numbers from experiments. Okay, so knowing what you guys know, let's start real simple. How many sig figs are in this very first number? How many significant figures are in the first number?
Four?
Are you sure?
No, I think it's three.
Okay, so the correct answer is 3, because this guy is just acting as a space holder, right? And all 3 of these numbers are significant. The 0 in the middle is significant because it's captured between the 2. So it's a trap 0. So always trap zeros count as significance. So those leading zeros don't count as significance. They're just placeholders. So what about this guy here? How many sig figs here?
5.
Are you sure? Think about what I just said.
But there's a decimal there. That's I would think that those 3 at
Yeah,
the
but
after the decimal count.
only if it was after the number, right? So if it was 25.00 and these zeros were here, these zeros would count. These zeros are just
Okay.
placeholders, right? They're letting us know that this value is really, really tiny. So they're just placeholders. They have to be there. Otherwise, we get the wrong value entirely. Does that make sense?
Yeah.
So this here is they have to be there. So yes, that's right. Alberto. That's true that there's 2 sig figs here, right? So for this guy, there would be 2 sig figs. For this guy, there would be how many sig figs? These were zeros.
4.
So this guy would be 4. And this guy would be 2.
Okay.
You guys see the difference?
Yeah.
So these zeros here, they're not going to count as significant. They're just placeholders, right? These leading zeros. Okay. Okay. Here. Okay. So we've talked about how we go about rounding off. Okay, so let's go ahead and do this problem. So here it says an example. Let's say a student weighs a beaker and 4 different chemicals using different balances. The individual masses and their sums are beaker, 319.5 grams. Chemical A, 20.460 grams. Chemical B, 0.0639 grams. Chemical C, 45.642 grams. Chemical D, 4.173 grams. And the total, the final answer of them all is 389.8393 grams. Okay, so let's put that down. Okay, so where would I draw the line for my answer here? Where would I draw my lines if I'm adding these all together? So for the first one,
After the 5.
after the 5. What about the next one?
After the 6.
After the 6. And the next one?
After the 9.
Okay, so you said the second one after the 6. Are you sure about that one?
No, it's after the 0 because it's after a number.
That's right. Okay. And then the next one would be after the 9. Okay, so which line are we going to use? A, B, or C?
A.
Going to use A. Okay, so you know the answer is, let's say, get the math for us. It's 389.8389 grams. Okay, so what am I going to use to round? Which number?
The 3.
The 3. Okay, so I'm going to use the 3. Am I rounding up or am I going to leave it alone? Am I going to leave the 8 alone or am I going to round it up?
Leave it alone.
Okay, so then my answer is going to be 89 point, you said leave it alone. Is there anything following that 8?
You would put 3 zeros, right?
No, if I put 3 zeros, that means that I have significance. Those numbers become significant. We're saying that we're only going up to that 8 in terms of, so that's where significant ends. So then we would just leave it as 389.8. Does that make sense? Because this number here,
Yes, it does.
the very first number, has only uncertainties till after that 5, right? So that means that we can't go, we're not sure about anything else because we don't know what follows that 5, right? So we don't know if this is really a 5 or is this just a 4.7, right? 0.47. This could really, instead of being 0.5, it could be 4.7, or it could be 0.4522, right? So we just know that it's greater than 5, right? The numbers that follow in here are greater than 5, potentially, right? And so it could be as low. So we're saying that this number here, this number really can be 319.45, 0.00001, or it could be 319 point 5 4 9 9 9 9. So it could be anywhere between there, right? We don't know because the person's scale only gave them 3.5. Does that make sense? So because this is so uncertain, it can be anywhere of these. That could change our numbers. That could be significant beyond here. We're really paying attention to that. So we have to tell people we're not sure about it. So then we only have 4 sig figs. So does that make sense? Did I just make it more confusing?
No, it makes sense.
Okay. Okay, so let's keep moving forward. Okay, so we talked about sig figs in terms of multiplication. So if we're multiplying two different numbers, we have to look at the number that has the least number of sig figs. So in this case, it says if the mass of 1.000 liters of gas is 1.436, what is the mass of 0.0573 liters? So the way that we would do this is we have a relationship, a ratio, right? So we know that 1.000 liters is equal to 1.436 grams. So if I'm starting out with 0.0573 liters, and I want to calculate the mass of that, I want it in grams, what am I going to use? So I'm going to use this
You're going to use your
equivalence.
ratio
That's right, I'm going to use this ratio. So if I want to get rid of liters and I want to get to grams, where does liters need to be?
on the bottom to cancel out.
Okay, so that's 1.000 liters, and we'd have grams on top. Okay, so then liters are going to cancel out, and then we're going to be left with just grams. Okay, so we get an answer of 0.0828. So here, if we're paying attention to significant figures, how many sig figs should we have?
Would it be 4 because we're going based off the grams?
Okay, would it be 4? Because grams have 4, but how many does our starting number have?
3.
3. So what is the rule about multiplication and division?
Go with a smaller one?
Smaller one. So isn't 3 smaller than 4?
Yes.
Okay, so then we know our answer should have 3 sig figs, right? So it should be 0.0823 grams. Because we use the 8 to determine whether we're rounding up or leaving it alone. Does that make sense?
Yes.
Okay. Okay. So the rules for let's see. So the rules for calculations. Okay, so we've already talked about the addition of subtraction. We also talked about multiplication and division. And we know that we have to use PEMDAS for it overall. So we've already gone over it. Let's see, let's move forward. Okay, so often we will have to, because we are in the US and we're very stuck in our ways about using the empirical system or the United States customary system. Because of that, we need to be able to convert often inches into centimeters, pounds into grams, gallons into liters. So these are our conversion factors for that. So if you guys look under your resource tab, there will be a tab that says chemical packet. On that packet, you can download all of those, print those out. I recommend that you print them out in color because they look so much better in color and they're clear in color. You can use those on your exam. So every exam that I give you guys, you can use that packet on them, okay? Okay, and a lot of them have the conversions because I am a strong believer because I believe that you can Google just about anything these days, right? Unfortunately, you can probably Google the answer to my latest test, you know, even though I have 15 new questions added on to it. So because I feel that you can Google the conversions, I don't care if you memorize them. I also feel that the more that you use them, the more that they stick up in your head. The least that you use them, then they don't stick up in your head. And so a test that would normally take you guys 40 minutes to complete will take you 3 hours to complete because you don't have them up. So I kind of leave it up to you. You have the sheet, you can look at the sheet. And if you've never looked at the sheet, then you're going to struggle using the sheet. So the more you use the sheet, the better you get with it, the faster you get to it. And then it's just like a crutch, right? You don't really need it, but you have it there just in case. Okay, you guys understand? Okay, so in other words, you guys have, well, a conversion sheet, or AKA a cheat sheet or a cheat packet that you guys can use on every exam, right? That you didn't even have to write out yourself. You just got to use it. Okay, so knowing that, so these are some of the US customary conversion factors. So, you know, we know that 1 feet equals 12 inches, 1 yard equals 3 feet, 1 mile equals 5,280 feet. We know that a pound equals 16 ounces. We know that 1 quart equals 32 fluid ounces, 1 gallon equals 4 quarts. Okay, so we can use all of these conversions to sit there and help us get to where we want to go. So if we're getting something in quarts, we can get to liters, right? So we should be able to manipulate these to our advantage. Okay, so let's see if you guys can do that. a soft drink manufacturer is converting from the USCS units to the metric units. If the quart bottle initially is to remain at the same volume, what number of milliliters should be printed on the label? So 1 quart. So that would be our given. 1 quart is our given. So 1 QT. Okay, so oops. So how can I change 1 quart to milliliters? So go back to those conversions. Or if you guys have your conversion sheet. So I know that 1 gallon equals 4 quarts. So can I use that one? And I also know that 1 gallon equals 3.785411784 liters. Okay, so I know that 1 gallon equals 4 quarts. I also know that 1 gallon equals 3.78547. We're going to use that liters. Okay, so then gallons are going to cancel out. Cancel out different colors. Gallons are going to cancel out. Quarts are going to cancel out. And I'm going to be left with just liters. So what is my answer? We want milliliters. How many milliliters are in a liter? Okay, don't all you guys yell at me at once. Berto, help me out here. Are you there, Berto, or did you leave me? Looks like he's gone. Brittany, are you there? Okay, Bertha, are you there? Is anyone there? Knock, knock. That's part of teaching online. I can say anything I want to say. Nobody would ever know. Nobody's there. Okay.
1,000 milliliters in 1 liter.
Okay, thank you. So we know we have 1,000 milliliters in 1 liter. So then liters are going to cancel out and we'll be left with just milliliters. So we do the math. So let's see. So that 1 quart would be, quote, an exact number. These are conversions. This guy technically would have been an exact number. So we could use any sig figs that we want under these circumstances because we have all exact numbers. So sorry, not 0. Forgot to multiply it by 1,000. 946 milliliters. Okay. Okay. So let's talk about temperature. Okay, so the Fahrenheit scale is the scale that we use in the US. And so if we take a look at the equation at the bottom, this is basically using the Fahrenheit scale and converting to Celsius. Okay, so we can also change this equation around so that we can change the Celsius scale, which is the scale that is used by most other countries. So multiply both sides by 1.8. So that 1.8 is going to cancel out here. Let's see, 1.8. 1.8. So then we get TF minus 32 equals 1.8 times TC. So if we want to solve for TF, we get TF equals 1.8 TC. So if we add 32 to both sides, that's what we do to one side of the equation, we got to do to the other side of the equation. If you guys remember that from math. So we get 1.8. Okay, so now this was changing Celsius to Fahrenheit. Okay, so what I'd like you guys to do is, if we have 0 degrees Celsius, so our temperature is equal to 0 degrees Celsius. Calculate how much that would be in Fahrenheit. So we want to calculate TF. Okay, so which equation would I use? Would I use this equation here? The first one? Actually, I could use either one, technically, but one requires more work to shift it around. Which one would be easier for us to use? The converted one or the other one? And if you can do that, just do my calculations for me. And then I want you to do 212 in Fahrenheit, degrees Fahrenheit. Okay. So I'll give you guys a minute to sit there and kind of get your thoughts together. Give you 2 minutes. Okay, so if we went ahead and put 0 degrees in for our TC, so we have 1.8 times 0, which we know is going to be 0 plus 32. We get our TF, temperature in Fahrenheit, is going to be 32 degrees. So 0 degrees is the temperature that water freezes. So we know that if we have 32 degrees Fahrenheit, water is going to freeze. Okay, so let's see. So the next one I said use our TF is equal to 212 degrees Fahrenheit. So in this case, we're going to use this equation here. So we're solving for TC, or temperature in Celsius. So we plug in 212 minus 32 divided by 1.8. So if I get my math right, that'll be 180 over 1.8. Or we would get 100 degrees Celsius. So 100 degrees Celsius is the temperature that water boils. So 212 in Fahrenheit would be the same. Okay. So in chemistry, we're able to use all three measurements, but frequently we use another measurement called Kelvin. Kelvin is based upon the absolute scale. So the absolute scale basically is the point where at 0 degrees Kelvin, molecules stop moving. So pretty much anything stops moving. So those atoms basically stop moving at 0 degrees Celsius, at 0 degrees Kelvin. Okay. Another temperature scale that engineers often use in the US is called Rankins. Rankins is also based upon 0 degrees, based upon absolute zero, but it is based upon the Fahrenheit scale rather than the Celsius scale. So let's talk about Kelvin. That's the one that you're going to be responsible for. So the conversion factor from temperature in Kelvin is TC plus 273, and it actually should be 0.15. They did a little bit of a rounding there. Okay, so absolute zero is negative 273.15 degrees Celsius. So if we want to base it upon that scale, that absolute zero scale, then we basically have T Kelvin is going to be equal to C, or TC plus 273 degrees. Okay, so then that would convert us from Celsius to Kelvin. Okay, so if we have 0 degrees Kelvin, so then the only way that would work is if we have TC plus 273.15. So TC would equal negative 273.15 Kelvin. Okay. Okay, so now let's use this equation. If we have 0 degrees Celsius, so T degrees C equals 0. What is our temperature in Kelvin? So what is TK?
273.15.
273.15, that's right. Okay, so if TC was 100, what would be our degrees in Kelvin?
373.15.
Okay, let's see if we can make it a little more challenging. So what is the temperature of our bodies in Fahrenheit?
98.6 or something.
Okay, so it's 98.6 degrees Fahrenheit. Okay, so if you can do me a favor, I'd like you to change that to Celsius, and then I want you to change it to Kelvin. Okay. So if we're going to do that, which equation are we going to use to change from Fahrenheit to Celsius?
Degrees Celsius equals temperature Fahrenheit minus 32 over 1.8.
Okay. So TC equals TF minus 32 over 1.8. Okay, so we have 98.6 minus 32 over 1.8. We do that math, that is going to be 60.
37.
Oh, good
Oh,
job.
sorry.
No, that's all right. You're good. X 1.8. So that's going to be 37 degrees
Celsius.
Celsius. And so 37 degrees is a temperature that yeast likes growing at. And if we change that to Kelvin, which equation am I going to use?
TK equals Celsius plus 273.15.
Okay, so that equals,
310.15 Kelvin.
okay, 273. So you said it equals 30310.15.
No, 310.15 Kelvin.
Okay. Piece of cake. Okay, so that's how you use Kelvin, Celsius, and Fahrenheit, and how you're able to convert between all three of them. So this is just basically showing you the scales between the three scales. So at 212, water boils. That's 100 degrees Celsius. That's 373.15 degrees Kelvin. And then water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and 273.15 degrees Kelvin. Okay, so convert 288 degrees Kelvin to Fahrenheit. So first thing I'm going to do is to do what?
Convert it to Celsius.
Convert it to Celsius. So we have 288 Kelvin. So if I'm converting it to Celsius, what do I need to do?
I would use the same formula, the TK equals TC plus 273, and just subtract the 273.15 from each side.
Okay, so I use TK equals TC plus 273. 5, oops. So I get TK minus 273. 0.15. So 288 minus 273. 0.15.
$14.85.
Okay, and that's degrees Celsius. Okay, so we have 13.85. Okay, and then how do I convert that to Fahrenheit?
TF equals 1.8 times degrees Celsius plus 32.
Okay, so we have 1.8 times 13.85 plus 32.
$56.93.
Okay, piece of cake.
Dr. Henry, for conversion to Celsius, how did you get 13.85? I got 14.85.
Oh, my bad.
So that would change your final answer to 58.73.
Okay. Thank you for the correction. It's because I was trying to do it in my head. That's the reason why. And for some reason, my head is still on Monday. 58.73. Sure. Okay, sounds good. Plus, I'm just keeping you on your toes. Okay. Questions, concerns, other than my poor math skills? I got to use my calculator a little bit more. Okay, so here's the table. What I'd like you guys to do is fill in the table. Okay, so I'm going to put you guys in groups for about, we'll say 10 minutes. We'll say 15 minutes. So then you guys have a 5-minute bathroom break, and then you guys come together, finish out the table, and then we'll meet back together. Does that sound good? Okay, how did he go?
It went fine, but I have a question for the middle one, the Celsius.
Okay.
On that one, would we round it?
Yeah, you can go ahead and round it. And that's the thing about temperature, because the way the equations are set up, because how they're set up, you can set it, typically round your Celsius to whole numbers. I mean, your temperature to whole numbers.
Okay.
Okay. Okay. So what did you guys get for the first one in Fahrenheit?
Negative 13.
Okay. Kelvin?
248.15.
Okay. Okay, the second one in Celsius.
Because we round up, it would be 41.
Okay. And Kelvin?
314.15.
And the last one in Fahrenheit?
109.
109.
Because I got 108.62.
You got 108.
I don't know what I did. Yeah, I don't know what I did.
Okay, so the first thing that we should probably do is change this to Celsius, right?
Yeah.
So we change that to Celsius by subtracting. So 364 minus 273.15.
90.85 is the temp for Celsius then.
Set 90.85. Let's see. Okay. And then that's Celsius. And so we know that Celsius is going to be, it's plus 32. Plus 32. 1.8 plus 32. I'm sorry, 1.8 times 90.
Okay, so they're gonna send Joe an email right now, and they're just gonna confirm it.
195.53.
They should call.
195. 3. Okay. So if we round up to a whole number, okay.
Yeah.
Okay. Piece of cake. Okay, let's see. Okay, you guys have done good. So let's move forward. I think we're going to finish this chapter really nicely. Okay, so the next part is proportionality and density. Let me clear this. Okay, so when we talk about proportionality, we can talk about whether something is going to be directly proportional or indirectly proportional. Okay, directly proportional basically means that things are going to go up as they go up. I mean, so as one thing goes up, the other thing is going to go up. So let me give you an example. Okay, so if we have energy. So this is the equation for energy. Energy equals Planck's constant. This is a constant. And nu times nu. This is a Greek letter called nu. And I'll type this out for you guys as well. Okay, so nu is a Greek letter. Nu represents frequency. Okay, now frequency, because the wavelength of light or the wavelength of energy is wavelength of radiation can be measured in frequency, how frequent those wavelengths are coming by. So in other words, how frequent those waves are passing by would be our frequency. So as the frequency goes up, energy goes up, okay? As frequency goes down, energy goes down. Planck's constant is a constant. You guys know what a constant is, right? Yes, no, maybe?
Maybe.
Okay. A constant basically is a number that doesn't change. So this number is never going to be changing. So this means that energy is going to be directly proportional to frequency. So if my frequency goes up from 1 to 100, so we're saying if nu goes up, so this is our table for nu, then what's going to happen to our energy? So if we put in 1 for nu,
Your energy is going to go up.
my energy is going to go up by 100. Right? So if my frequency goes up from 1 to 100 to 1,000, then my energy is going to go up by 1,000. Okay, so because this guy is going to be 1H, this guy is going to be 100H. And this guy is going to be 1,000H. Okay, because H is just going to be a constant. It could be, it's a specific number that's never going to be changing. Okay, so this shows that energy is directly proportional to nu, or frequency. Energy is directly proportional to the frequency. Okay, so as energy goes up, the frequency goes up. Now, if we have the speed of light is equal to lambda, which is the wavelength, times nu. Now, the speed of light is also a constant. The speed of light is always going to be exactly the same. So the speed of light is going to equal 3.00 times 10 to the 8th power meters per second. Okay, so the speed of light is always going to be that value. It's a constant. So if the frequency goes up, so if nu goes up, nu increases, what do we expect to happen to lambda?
So it would increase as well?
Sure.
Oh, no, because you said that's the constant, right? So it's going to stay the same?
Well, C is going to be the constant.
Oh,
So if we're going to always get this value, if frequency goes up, then what must happen to nu? Happen to lambda. If nu goes up, what happens to lambda? Do we expect it to go up or go down? Well, let's put some values in here, right? So since we know that C is going to be 3.00 times 10 to the 8th, we're going to go ahead and use that one, okay? So if we say that lambda, so we'll say nu is, 10 to the 8th. So then what must be lambda if nu is 10 to the 8th? Lambda would be what? 10 to the 8th. And this is 1 over seconds. So if we go ahead and plug that into this equation, we get C is going to equal to 3.00 times 10 to the 8th meters per second. If we were solving for nu, we would just get C divided by nu equals lambda. Can you guys see that in the corner? Do you mind if I erase this part here about the energy?
Yeah.
We'll come back to it here in a second. And that from the right. Okay, so this is what this equation is saying, right? Because we said that C is always going to be the same number all the time, right? A little trouble with my. Okay, so this is what our equation is saying. So this is new down here. Fix this. Okay. So if we solve for lambda, we put in, if lambda here is, I'm sorry, if nu is 10 to the 8th, we put in 10 to the 8th for this equation. So we get 3.00 times 10 to the 8th meters per second. We divide that by 10 to the 8th, 1 over seconds. So this is going to equal 3.0, right? Meters. Okay, so let's say we increase nu by 10. So instead of making it 10 to the 8th, we make it 10 to the 9th. So then lambda is going to equal, I'm going to put this here. .00 times 10 to the 8th meters per second over 10 to the 9th, 1 over seconds. It's an S. So this guy's going to equal now 0.0, oops, sorry, 0.300 meters. Okay, so we went from 10 to the 8th to 10 to the 9th for nu. So we're increasing nu, right? So as nu increases, what happened to lambda? We went from 3 meters to 0.3 meters.
It decreased.
It decreased, okay? So this means that in this equation, lambda, which is the wavelength, is indirectly proportional to the frequency. So as the frequency increases, the wavelength decreases, okay? And that was different than the energy, because we knew that the energy increased as frequency increases, okay? So this guy here, if they're directly to each other, right, they're going to be indirectly proportional to each other, right? If we take a look, we had energy equals Planck's constant times nu. If they're on the opposite side of the equation, right, and they're even to each other, they're not 1 over it, then they're going to be directly proportional. As one increases, the other one's. Here, these guys are on the same side of the equations, directly to each other. They're going to be indirectly proportional. Okay? Does that make sense? Or another way of looking at it, if we solve for the constant, because the constant is always going to be the same. In this case, Planck's constant is always going to be the same. So we have H equals E over nu, right? So if we get the equation in this form, they have to be, for the number to be always the same, as this guy increases, this guy has to increase. Where here, this is another constant, where C is the constant. These guys have to be indirectly proportional. So this guy is indirect. And this guy is direct. Okay, direct meaning as one goes up, the other one is going to go up, right? Okay, so now this is going to be important. You're going to see these equations throughout everything. So you need to just sit there and play with it a little bit, right? If they tell you that one thing is going to be a constant, Planck's constant, so just assume that that's not going to change in value. If that's not going to change in value, then look at the other players. Are they going to be directly proportional to each other? Or are they going to be indirectly proportional to each other? And that's going to be kind of important for us to understand how equations work, okay? And so you're going to see tons and tons of little equations that you guys have encountered, or you should have encountered at this point. If you haven't, it's okay. Just look at it. We have to determine whether it's directly proportional or indirectly proportional, okay? Okay, so let me kind of explain this to you in terms of density. Okay, let me clear my screen. Okay, so density, we're basically saying we're trying to find a way of converting, making mass equivalent to volume, right? So the way that we do that is by using density. Density is equal to mass over volume. Now, density is a constant. It doesn't change value unless we change temperature drastically, right? So the density of water is always going to be 1 gram per milliliter as long as we're around 25 degrees Celsius, okay? So it's always going to be the same. So the density is always going to be the same at room temperature, water. So whether you have 3 liters of water, or you have 20 gallons of water, or you have 35 ounces of water, the density is always going to be the same, okay? So which is going to be 1 gram per milliliter of water. Let me type that. Okay, it's always going to be the same at room temperature. Okay, long as we don't change the temperature, we don't make gas, we don't make water into steam, we're okay, right? It's going to be about 1 gram per milliliter. Okay, so that's going to be our constant. So density is a constant value. Now the things that can change is our mass and our volume. So as I was saying, if I have, let's do a little table here. If I have mass, volume. Okay, so we know that the density of water is 1 gram per milliliter. Okay, so let's say I have 1 gram. So my volume is going to be what? If my density is always going to be 1 gram per milliliter. So what is going to be my volume? In this case,
Milliliters?
it's going to be 1 milliliter, right? Okay, so if my mass is 100 grams, what's going to be my volume?
10 milliliters?
Sure. So if it's always going to be equal to 1 gram per milliliter, and I just told you that I have 100 grams,
Then you have 100 milliliters.
then I have to have 100 milliliters, right?
Mhm.
So if I have 2,000 grams, how many milliliters would that be?
2,000 milliliters.
2,000 milliliters. Okay, so as my mass goes up, my volume has to go up proportionally. Does that make sense? Yes or no? Okay, so my mass went up to 100, my volume went up to 100. My mass went up to 2,000, my volume went up to 2,000. Okay, so as my mass goes up, my volume has to go up proportionally to that, to whatever my constant value is. If my density was 0.5, let's say D equals 0.5, D representing density, then my volume would go up by half. So instead of this guy being 1 now, the volume would be now 0.5, right? Make sure. I'm sorry, my volume would be 2. It would have to go up by twice the amount being divided by. So if my density is equal to 0.5, then let's solve for this for B, right? So density is 0.5, then my mass over density is going to equal to my volume, right? So then that means that if I have 1 gram of whatever, we'll say it's, I don't know what's 0.5. I have to look. I can't remember off the top of my head. We have some chemical that has 0.5 density, right? So then in that case, if I have 1 gram and my density is always going to be the same, which is 0.5 in this case, then my volume is going to be 2. So then in this case, this is density of 1. D equals 1. This is D, different chemical, D equals 0.5. Okay, so then as 1 gram, then my volume has to double. So then my volume is going to be 2 milliliters. Okay, if I have 100 grams, then my volume is going to be 200 milliliters. But the trend is still the same. As my mass goes up, my volume has to go up proportional to what my density is. Okay, and that's the take-home message. So at the end of the day, you have this equation. Density equals mass over volume, where density is going to be a constant value. Okay. We're almost done. Last 7 slides. Okay. So density is often going to be expressed in grams per milliliter, grams per cubic centimeter. We know that 1 milliliter is the same thing as 1 cubic centimeter. We talked about that. Density is also going to be dependent on temperature. So it's going to change if the temperature changes. Water becomes less dense when we increase the temperature. When it becomes a steam, it's less dense. Okay. Let's see. Okay, so here, this is ice and this is water. And so with ice, we know that if we put ice in water, ice floats, right? And the reason why is because ice is less dense than water. And that's because the organization, because it's organized, it actually leaves these little gaps of air pockets for water. I mean, so that air gets in there. And so water will be less dense. Ice will be less dense than water, and hence it's going to float because you have those air pockets, not as compact. Where in the case of the water molecules, you don't have those air pockets, right? And so that space is being occupied by water molecules. And so ice is always going to float on water. And so that's partially why, let's say an an iceberg floats, right? And it doesn't freeze the entire thing. So ice will be at the top of the river or the top of the ocean. The iceberg will be at the top of the ocean, and the fish will be okay at the very bottom because they don't freeze to death, because it still will be water at the bottom, but the ice is going to be up top. Okay. So because of the factor that ice floats on water, life is able to survive underneath that ice. Okay. So if you guys get a question like, explain why life is able to survive in water when it freezes, then you guys know it's because of the density. Okay, so here, this is basically showing us that ice floats on water, where in the case of if we freeze do you guys know what ethanol is? Anyone? Ethanol is an alcohol. It's actually drinking alcohol. It's what we use to, well, vodka or whiskey, or, so it is the alcohol component in whiskey, the alcohol component in vodka. Okay, so if we freeze ethanol solid, a complete thing of ethanol, it'll actually sink to the bottom and it won't float in ethanol. Okay, because the solid is more dense than the liquid. So it doesn't float. Where water, the solid, ice, is less dense than the liquid. Okay, and that's because of how water forms those nice little pockets, and that's going to be due to what we call polarization. And we'll be talking about that later on. Okay, so if I put a log on a river, does it float or does it sink? Anyone? Okay, so a log on a river is going to float. Okay, and that's because it's less dense than the water itself. So log, so depending on the type of wood we're working with, pine is 0.5, maple is 0.6, oak is 0.8, all of which are less dense than water. And so these guys would float on top of water. Where glass is 2.5. It's not going to float. It's going to sink to the bottom. Okay. Okay, so these are some of the common densities of substances that we run across. Okay, so let's use this information to answer this question. The mass of a 50.00 milliliter sample of methanol is 39.59 grams. Determine the density of methanol. So what is the equation for density? Sam? Samantha? Anyone? Okay. I guess we're all recording, but not there. So the density is equal to mass over volume. So if the mass is 39.59 grams, then the volume is 50.00 milliliters. We have four significant figures for both. So my answer should also end up with 4 significant figures. So if I go ahead and do that math, 0.7918 grams per milliliter. And again, 4 significant figures, and then that provides me with my density. Okay, our next question. So the density of a certain machine oil is 0.910 grams per milliliter. So find the volume. We are given our density already. So find the volume occupied by 196 grams of that oil. So our given in this case is going to be 196 grams. Okay, so if we start off with our given, and we can use this as an equivalency. So 0.910 grams per milliliter is going to be our equivalency. Okay, start with our given. 196 grams. So I know I want to get rid of grams. So I want to put the grams on the bottom and I want to put the volume on top. So we have 0.910 grams. And we know that per milliliter means per 1 milliliter. So I'm saying 1 milliliter on top. So 1 mil. So grams are going to cancel out. And then we're going to be left with milliliters. So we do that math. So we're going to get 215.384615 grams. Oh, sorry, milliliters. But I know that I want 3 sig figs because my given was 3 sig figs. 1, 2, 3. So then my answer with 3 significant figures, we're going to use the 3 to determine whether we're going to round up or leave it alone. So 3 is less than 5, so we're going to leave it alone. So my answer should be 215 milliliters. Okay. Questions? Okay, keep going. Okay, so things to remember. So things you want to remember when we talk about density, the mass density is going to equal mass over volume, which basically means that as mass increases, our volume is going to have to increase in terms of density. So if I go from 1, let's say a volume of 1 to a volume of 15, then my mass is going to have to increase by that same amount. Okay, so because they're directly proportional with each other. Okay, the other thing to keep in mind when you're doing these problems is to work enough problems that you guys get a clear understanding. So if you guys are on chapter 4, this is chapter 4's work. So you guys should be able to complete it at this point. Try to make sure that you guys are getting the problems and understanding the problems. Use the fact that you're canceling out units to help you orient things. Even if you're not familiar with the equations, if you look at the units, they could actually help you solve the problem. Okay, questions? Concerns? Cash? Okay, then I guess I'll see you guys on Friday. Have a good day.
Dr. Henry, I was just curious, what will we need for Friday's lab?
I have to take a look. I'm a little rusty. I'll send an email out, But if you've gotten everything that I told you to buy, there won't be anything else left for you to buy. Okay.
Okay.
So the key is to buy it all, and then I'll be able to tell you instantly. Okay. But I'll take a look at it because I have to make some modifications to your labs because there are certain things that you guys have in your kit now that you didn't have before. So that gives me a little more flexibility. So,
Okay.
okay.
Thank you.
Okay. You guys have a good day, and I'm looking forward to seeing you guys on Friday. Any other questions?
I have a question.
Okay.
Okay, for the lab, for the Mentos and the Coke, so you want us to record it and put it on YouTube, or just like put it on like the data, the one that you posted, like to put all the information.
Okay. So you have to do both. You have to put the data
Okay.
into the table, and you also have to record it and post it because you weren't there doing the lab with me. So I don't know if you did it or not. And so I need you to be there to either do the lab with me, or if you guys are doing it on your own, which is fine, either one is fine. You have to just show me that you've done the lab. Okay.
Okay.
So part of your points are going to be attributed to you doing the lab physically.
Okay.
Okay.
Yeah. Thank you.
Good question though. Okay. Any other questions? Okay, I will see you guys on Friday then. You guys have a good day.